We all know how to add numbers together if we're using decimal. If we want to add 19 plus 3, 9 plus 3 is 12. We put the 2's down here and we carry the 1's up to here. Then we do 1 plus 1 plus 2 gives us 4, and we get 42. But how do we add numbers like this inside of a computer? How does the computer perform this operation? Well, computers work in binary. So we can't represent 19 and 23 using 1923. We have to use binary digits, which is simply 0 and 1. So the numbers that we have here, the 10011, is 19 in binary, and 10111 is 23 in binary. The way that we add them together is exactly the same. Just as we added 9 and 3 first, the least significant digit, we start over here with the least significant digit and we add the two 1's together. So 1 plus 1 is 2. 2 in binary is 1, 0. So we put the 0 down here and carry the 1 up here. We then add 1 plus 1 plus 1, and this gives us 3. 3 in binary is 1, 1. So we put the least significant one here, and we put the most significant one here. 1 plus 0 plus 1 is again 2, which is 1, 0 in binary. 1 plus 0 plus 0 is 1, and 1 plus 1 is again 1, 0. So the process is exactly the same. We just have to remember all of the possible additions between 3 bits, which is either going to be 0, 1, 2, or 3, and we write those out in binary. If we just consider the case where there's no carry, we have these 4 possibilities. 0 plus 0 is, of course, 0. 0 plus 1 is 1, and 1 plus 0 is 1. And then 1 plus 1 is 2, or 1, 0 in binary. If we then consider the case where we have a carry in, we simply need to add in the 3 digits. So 1 plus 0 plus 0 is 1. 1 plus 0 plus 1 is 1, 0. 1 plus 1 plus 0 is again 1, 0, in other words 2. And finally 1 plus 1 plus 1 is 3, which in binary is 1, 1. And so from this we have all of the possible combinations. So if we just focus on these first 4 cases here, so these first 4 here, now these are the case where we had no carry in. So for example, we have 1 plus 1 here, which produced 1, 0. And this is the case that we had in the first column here. So there was no carry in. 1 plus 1 produced a 0 and a 1 as a carry. So it produced a 0 and then a 1 as a carry. If we look at the pattern here, we see we get a 1 if one of the 2 inputs is a 1, but not when both are a 1. And this is what we call an exclusive OR. In our case, we'll have 2 inputs and 1 output. So these 2 inputs here are these 2 bits here. So a bit, binary digit, we have 2 bits coming in, and we have a single bit coming out, which will be 0, 1, 1, 0, depending on the input. We also want to consider the carry out. Well, the carry out is only true, is only 1, when we have both inputs 1. So input A and input B are both 1. So that's an AND. So both inputs must be a 1, and we will produce a carry. Okay, so again, this is an exclusive OR, which we often write as just XOR, and this is an AND gate. And we want to tie, it's the same inputs. So if we call this column here, I'll call this A, and we'll call this column here B. So I'm going to put A and B coming into here, and our inputs come down there. Now, we have the sum and the carry produced at our outputs here, but only for the case where there's no carry in. So we want to add the case where there's a carry in. And we'll call this column here, we'll call this our carry in column, which was 0 for all of these cases, but is now going to be 1 in these cases. Well, we already have the case for 0, so when carry in here is a 1, we simply need to add that into our result. So we can just do carry in plus the result of our addition. So I'm going to put another exclusive OR here to give our sum. And I'm going to add in our carry. So remember, this up here is just A plus B. So A plus B here is coming out of our exclusive OR, and that gives us this right-hand column here. And we have one of the carries here. And so this out at the output here, this is our sum, which I'll call S. So this is our S column, and this column here I will call carry out, CO for carry out. So how do we do the carry out column? Well, if carry in is a 0, it was just A and B. But down here, if carry in is a 1, it's also A and B. So it doesn't matter what the carry in is. If A and B are both 1s, then we'll get a carry out here. But we also need to account for these two cases. So these two cases here are where the sum, so the result of our sum here, so if I just put brackets around the sum portion, so if the result of this sum is a 1 and our carry in is a 1, then we get a carry. So that's saying the result, our A and B result up here, and our carry in. So the output here accounts for these two ones, and the output here accounts for this one and this one. And so we get a carry on our output if either this case or this case is true. So we can just use an OR gate for that. And that produces our carry out. So this circuit here, this is what we refer to as a full adder. And we can use this circuit here to add 1-bit numbers. So the next thing that we want to do is to chain these together to be able to add more than just 1 bit. We want to be able to add multiple bits. And the way we can do that is by taking this carry out and feeding it in. Notice that when we add the numbers here, the carry out from this feeds into the next addition, and then we add these numbers, and the carry out then feeds into the next. We add these, the carry out feeds into the next. So if we have multiple full adders, we can take the carry out from one and feed it into the carry in of the next. The next step is to bring our circuit sketch into KiCad. I'll do that by drawing the schematic, and we'll start by adding the exclusive OR. So I'll hit A and search for XOR. And you can see that it's come up with 74HC86. The 74HC86 is the chip that I'll be using. If I zoom in here, you can see that we have the exclusive OR symbol. In fact, there are 4 exclusive ORs inside of this one chip. So we have A, B, C, and D, which are all exclusive ORs, and E is just a power input. So our VCC and ground. So I'll place component A, and this will give us one of our exclusive ORs. We can then place another one, because we need 2 of these. I'll place this one over here. And I have the datasheet here for the exclusive OR gates. So this is the datasheet for the 74LS86. And it's one of these little chips here. So the pins on this chip, the physical pins here, line up with this diagram here. But because we're using KiCad, we don't actually need to worry about that. KiCad will make sure that we wire up to the correct points for us. Next, we want to place an AND gate. So I'll hit A again here, and we'll search for AND, and we should get 74 series. AND, of course, is a common word, makes it a little bit harder for us to find it. But if we open up 74, here we go, 74XX, and we search through here, we should get quad 2 input AND. Where are we? So here we go, 74LS08 is a quad AND 2, or a quad 2 input AND gate, and we can see indeed we have our 2 input AND gates. Again, we have the 4 units and the power. So I'll place these over here, and this will produce our carry. So I also have the data sheet for this one. If we have a look, very similar to the previous one. The pin layout's in basically the same configuration. We have 2 inputs to each AND gate and 1 output, and then 4 of them. And so when we build the PCB, our chip here, our 74LS08, the pins on here will be wired up to the appropriate AND gates on the printed circuit board. Finally, we need our OR gate. So I'll add with A, we'll look for an OR. I'll have to search again for our 7.4 series chips. So we have 7.4 here, quad 2 input OR gate, which is this one here. So we have our quad 2 input OR gate. Okay, so we can see we have our OR gate here, and again it's a quad, so we have 4 units and power. So we'll place one of those. I'll just place that at the end here. And now we can wire up. So we've got all of our gates. If we put the wires in, we can see we need a connection from the output of this exclusive OR into the next. So I just hover over here and press W for wire, and we can hook that up like so. We then want the output of this AND gate going into the OR gate. So again, W for wire, and we'll just route around here. The output of this AND gate also feeds into our OR, and I'll just continue on and quickly wire all of these together. So now that we have all the wires, I'll put some labels on here so that we know what each of these inputs and outputs is. So we start up here, I'll hit L to insert a label, and this is just our A input. Now this is going to be the input of our least significant bit, so I'll call it A0 so that we know that it's the least significant bit. I'll put another label down here, and that will be our B0. And then our label here will be our C0, our initial carry in. Notice this is C0, not CO for out, so this is our first carry in. Our carry out will be over here. I'll put a label up here as well, and this will be our sum 0, so the 0th bit of our sum. And we just want that right aligned, and then we'll place that up here. Now that we've got the whole circuit, we don't need our overlay here anymore. I'll get rid of that to clean up some space. And we have our 1-bit full adder. Okay, now that we have our circuit, I'll just select everything and just move it up to make a bit of space, and we can start to duplicate. So I'm just making copies of these. Control D or Command D will let us duplicate whatever we have selected. In fact, I'll just move that down a little bit. And I'm going to do a 4-bit adder, so I'll copy this 4 times. Notice that we have the letter A and B up here against each of these exclusive OR gates, and down here it's also A and B. That's not quite what we want. We need to change this to A, B, C, and D because we have 4 exclusive ORs on one of our 7486 chips. So I'm going to just edit this one, and I'll say that it is unit C, and then I'll edit this one here. We can just hit E to edit when we're hovering over something. I'll change that to be D, and now we have A, B, C, and D, and I'll just do the same thing down here. And then we need to do the same thing for our AND gate. So we've got A, B, we want this to be C, and D. Finally, all of our OR gates are currently unit A. We'll make them all different, and then we'll just need a single chip on the output for our 4 OR gates. So this is everything we need for our 4 bits, but we need to feed the output of the carry to the carry in down here. We also need to change all of the input labels. So I'll edit these labels. These should be A1 and B1 and so on. Okay, the next thing we need to do is wire our carry out. I'll just replace this one here. So we'll wire around here and then hook it in to our carry in. So now we are feeding out from our first full adder here, the carry out from there. So this is our least significant bit. So the carry out of the least significant bit becomes the carry in to our next bit. So I'll wire the rest of those up as well. And now we have most of our circuit. The one thing that we are missing here is a carry out label. So I'll put a label on there for carry out. In fact, I'll call it C4 rather than carry out. And this tells us that we can actually have more full adders down here if we like. So we have a C0, which is our initial carry in, and a C4 for our carry out. Our initial C0, I'll just connect that to a constant 0. So we're never carrying anything in. And I can do that by tying it to ground. So if I press P, we get our power, and I can search for ground, and I'll just place a ground connection in here. And now our carry out is connected to ground. Okay, so this is our series of full adders connected together. So we have here a 4-bit adder. So I've just realized I've got the wrong numbering here. We've got unit 1 and unit 1. That means that these two exclusive ORs will come from the same integrated circuit. We have a look here. So if we have a look here, this chip here will be unit 1, which will probably be this one here. This chip here will be unit 2, but we want these two to come from these two chips here. So I'm going to need to, if I just zoom in so we can see what we're doing, I'm going to need to make these two down here unit 1. So if I just double click on the number there, I can change that. And now these 4 exclusive ORs will all come from the same chip. We also want to do that for our AND gate here. So I need to make sure that these are all the same. So I'll change these to all be unit 2. Do the same down on these next ones. This should be units 3, and our AND gate can be unit 4. Finally, our OR gates should all come from the same chip. So I'll make sure that these 4 OR gates are being used for all of our OR gates here. We'll call this unit 5. Right, so now we have all of our chips, we have all of our full adders. The only thing we don't have is power. Sorry, going back to here, if we have a look on here, we can see that our VCC and ground pins, so pin 14 and pin 7, need to be connected up. And there's a special component for that. So I'll add those power connections in. If I open up our component here, unit E here provides our power and ground, our VCC and ground. And this is automatically selected unit 1E. And if I duplicate that guy, it should automatically, it's given us unit 3E and then 6E. So we're going to have to renumber these. So I'll just change that to be 2, 3, 4, and 5. So that covers our 2 exclusive OR, 2 AND gates, and our OR gate. So now we have these 2 connections, which we can connect up some wires here. That's easy enough to do. We will just hit W again to put a wire right through there and connect all of those, and a wire across to connect all of these. Then if we hit P for power, we can select our ground, and I'll put the ground connection in down here. Let's zoom in so we can see what we're doing. And similarly, I'll connect up the VCC up here. So now we have power to all of our chips. The next thing we want to do is to add some switches. The switches will be our A and B inputs. So they will actually connect up to our A0, B0, A1, B1, and so on. So A to add some of those. So I want a switch, and I specifically want a dip switch. We want 4. We want 4 for our A inputs, and then we'll do 4 more for our B inputs. So that'll be switch for A, and I'll put another one down here for B. So wire these up. And I'll put our labels on here. So the labels I'll put here. So the first one, we can call that A0 and put it there. And by the way, R rotates to move it around, or we can select the right and left aligned here as we see fit. So A1, A2 and A3. And these will be B0 through to B3. Because I've put these labels on here, we don't actually need to run a wire from A0 around to A0 here. Having the same name, the same label on these two connections means there is a virtual wire coming through here. When we go to design the PCB, that will automatically be connected. So we've actually connected all of our switches up now to these inputs. So the switches we're going to use are these little guys here. And you can see that in the up position, it will be on. So if I flick one of these switches, so for example, switch 4, if I flick that up, it'll snap up and that will be on. If I snap it down, it will be off. On simply means the switch here is closed, and in this lower position here, it means all of them are open. So currently in this diagram, we have them all open. Open, we want that to mean 0. So the way that we can do that is by pulling all of these connections here down to ground normally, and then when we close the switch, we'll have it pulled up to VCC. So to pull that up, run a wire through here and connect those, and we'll put a VCC connection in. And I'll do the same here. We can wire all of those straight through. So when we close the switch, all of these will become a 1 or a VCC. And to make them a 0, normally we need to pull them to ground, and we'll do that through a resistor. So I'll add some resistors. Move these guys over. And what we want is just a standard resistor, which is just this guy here. And I'll need one for each of these connections. To try and keep it neat, I'll place these over here. And I'll put a ground. We can put a common ground connection here with power, ground, and then wire those up. And I'll place 4 more for the other switches, and then wire those as well. So now the way this works is when the switch is down, it is off. So these are open. So all of these are only connected to ground through these resistors. There's no current flowing anywhere, and so the value will simply be ground. As soon as we close this, we'll get a current flowing from VCC through to ground. A current flowing through a resistor means that there is a voltage across the resistor. In this case, all of any of these that are closed will be connected to VCC, meaning we will have a higher voltage on these A0 through to A3. We now need the same down here, so I'll copy that across. And now we have our switches wired up. The next thing we want to do is to connect up our LEDs on the outputs, and these will be connected to our sum outputs as well as one LED for our carry output. Again, I'm just going to use labels so that I can put our LEDs all together over here. And so our labels are just S0 through to S3 and C4 for our carry. So I'm going to add an LED. So we're just going to use this one here, and I'll add 4 of these. I'll just hit R to rotate that into a more convenient direction. We'll need some resistors here, so I'll place some more resistors. In fact, what I might just do is I'll copy these and we'll wire these up. The top here needs to have a wire to S0. We'll wire this one up to S1 and then wire the rest together, and then we can wire these down to ground. Now I'll place one more. I'll just copy these because we want to have one for our carry out. which we called C4. So now we have outputs for our LEDs. We have inputs for our A and B values. The last thing we need to do is actually provide power. So I've said we have VCC and ground, but where's that power coming from? So I've got a little bit of space down here. The last thing I'll do is place power from USB. Now I can use one of these USB-A connectors. If we look underneath here, we can see a few pins. These 4 pins provide power and data. So the 2 on the outside will give us power. We don't need to use the data pins, but we can power our circuit from a USB cable. We'll click A and we'll look for USB. So we want USB-A, but we want just a very basic USB-A. Let's have a look at the symbol here. We have a ground, we have a power, and we have the data. We'll just not connect the data and we can connect these 2. Okay, and we'll place this here. We can just connect power of VCC and ground, and then wire them together. Now, because we're not using these other 3 pins, we need to tell KiCad that we're not going to connect them. The way we do that is there's this not connected option over here, and I'll place those not connected values on these wires. And that is our full circuit. What I might do is I might just neaten this up a little bit. Okay, I've rearranged things slightly just to try and make them a little bit neater. A few things to note. I've also added in some capacitors here. It's a good idea to have capacitors with every power supply to every chip, and that just means if your voltage supply is a bit wonky, it'll help to smooth that out. Otherwise, everything's pretty much the same, just laid out a bit differently. I've also gone ahead and prepared the PCB. I'm not going to go through in this video how to do a PCB layout. I think that's a topic for a whole series of videos in and of itself. In KiCad, we can have a look at the 3D viewer, which gives us a nice view of our printed circuit board. So this is what our circuit board is going to look like when it is complete. We have our switches for activating components. We have our integrated circuits for our AND, OR, and exclusive OR chips. And I've put labels on here so that we know which chip we are connecting to, or rather which chip we are inserting into the board. So I'll order this PCB and then we'll put it together and see if it works. Our printed circuit board has arrived along with all of the components. So let's just check we've got everything here. The 2 switches here, we have our dip switches. I've also got all of these sockets, and I'll solder the sockets in, and that way if I make a mistake or I need to remove something, I'm only damaging sockets, and it will save the integrated circuits on these chips. So I'll solder those in and then I can just plug these guys in to the sockets. We have our 7408s here. That's these 2 chips here. That's our AND gates. We have our 7486 chips here. That's these 2. They are the exclusive OR gates. And then we have our single 74HZ 32 chip here, which is our OR gate to combine our carry-out signals. We've got some little LEDs here and the current limiting resistors that we'll use for those, and they'll connect up to this section. I've got the capacitors here. They're just some small capacitors, and they'll go to each of these spots next to each of the chips where they're being powered. Got the USB connector to go in here, and then we have the pull-down resistors that will make our inputs usually 0 unless we flick the switch on. So that's all of our components, and it's time to get soldering. I'll start by soldering in all of the passive components. I've got all the capacitors and resistors in, so the next job is to put in the LEDs. It's important to notice that one leg is longer than the other. The long leg is our anode, or the positive end, and the short leg is the cathode. So we just need to make sure we put them the correct way around. And the little square pad that we can see on here, that tells us which side is ground. So that's our negative end. And so I'll put this in that way with the short leg going into the square hole. Next, we'll put in the sockets for our integrated circuits. And when we're soldering larger components like this integrated circuit socket, it's a good idea to solder one pin on the corner, pushing down nice and hard, and then the other pin on the diagonally opposite corner, pushing down again fairly firmly. And that locks it into place, and now that socket is nice and secure, and we know that it's going to be in place properly. Then we can go ahead and just solder up the rest of the pins. Next, we'll put in the little switches here, the dip switches. And the final thing that needs soldering in is our USB connector. Now notice it has these two larger holes down the bottom here. That's for these tabs here. So the tabs on either side, they will mechanically hold it in place. They don't actually need to be electrically connected. And now we're ready to insert all of the integrated circuits into the sockets. So just paying attention to the numbering here. So this is the 74LS08 and our 74, we're actually using an HCT08. In fact, all of our components are HCT08, so our labels up here are not all correct. But the LS and HC and HCT chips are equivalent. So I'll insert those. Notice that there is a little half moon here, and that lines up with the half moon on our, if we have a look there, the half moon on our printed circuit board. So I'll insert these. Right, so I've got all of the components installed onto the PCB. And I have some USB power coming in, so this provides our 5 volts needed for all of our logic gates on our integrated circuits here. So let's test it out. If I put, so we've got A0 here, so if I put this up, that's going to be a 1. All of these are 0, so we have 1 plus 0, which is indeed 1. Note that S0 here is our least significant bit, and then we have our next least significant bit is a 2. So this represents 1, 2, 4, 8. Note that they are powers of 2. So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. All right, if we add, let's add another one. So if I move this guy up, then we have 2. So 1 plus 1 is 2. Looking good so far. Let's do a 3. So 1 and 1, so this is 1 plus 2, it's 3, so we have 3 plus 1, and we have our 4's place lit up, so that's looking good as well. So it's only a 4-bit adder, so the biggest number that we can represent is 15. But what happens if we add 15 to 15? Well, let's just turn all of these on to 15. So now B is 15, A is 15. Now obviously 15 plus 15 should be 30. You'll see up here our carry out flag has shown up. So this LED is turning on, meaning that we have a carry out. So what we get should add up to 30 if we add in 16. So the carry out is actually representing the value 16 in this case, one more than the 15 that we can get to. So we have nothing on 1, but we have a 2, 4 and an 8. Well, 2 plus 4 plus 8, which equals 14. So we have 14 plus 16, which is indeed 30. So we can see that it's working, but we have reached our limit. 30 is the biggest number we can represent with this circuit. What I'd like to do is build a 32-bit RISC-V CPU. This, of course, is not going to be enough for that. We need a 32-bit adder. So the next thing I'd like to do is build a 32-bit adder, and we can use what we've learned here in order to do that.